and we welcome Lou to give a talk on knot theory.
Sounds like it. Okay, here we go. I'll share my screen. And I'm going to talk today about virtual knot cobordism. And in the process, I'm going to review virtual knot theory quickly, and then I'm going to introduce some invariants, and we'll talk about virtual knot cobordism. That's the intent here. Let me see if I can get a full screen for this. There. All right. So let's begin by reviewing virtual knot theory. Virtual knot theory studies stabilized knots in thickened surfaces. So you have a knot in a thickened surface or a knot diagram drawn on a surface, and you don't care about the handle structure in the surface that isn't involved with the knot. You're allowed to cut it out and replace it. So one way of understanding that is to take a neighborhood of the knot, like the abstract neighborhood that I've drawn over on the right, and you're allowed to excise that from the surface and put that neighborhood back into any other surface you like. That takes care of the stabilization from the diagrammatic point of view. And if you think about an abstract neighborhood of that kind, then it naturally projects, because it's an oriented ribbon surface, it naturally projects to the plane and gives us a virtual diagram where the places where the ribbons go over or under one another, and I don't care whether they go over or under, since it's an abstract surface, they're projected to virtual crossings in the plane. And conversely, given a virtual diagram of that kind, we can take an abstract surface for it and add disks to its boundary and come back to a knot embedded in a surface. So I've illustrated in this slide taking the neighborhood of a knot diagram in a torus and then removing it and getting rid of some twists because I don't care about them, and I have a nice flat version of it which I can project into the plane. Or conversely, given one in the plane, I can form the neighborhood and put it into a surface. It's of interest, if you're doing examples, to see how to get at the genus of the surface that you make by forming the abstract surface. And as you see from this slide, if you form it, then there will be some number of boundary components, call it L. And then by examining the Euler formula, you can conclude that the genus of the surface obtained by adding disks to the boundary will be 1 plus v minus L over 2, where v is the number of nodes, real crossings, in the diagram that you started with. That, of course, is not necessarily the very least surface that the knot will bound, but it is the least surface that you can make from the given diagram. So this calculation is useful in working with examples. You can also think of them, the virtual knots, in terms of their signed Gauss codes, and then you can look at them abstractly as signed Gauss codes up to Reidemeister moves on the codes, or other coded situations that are useful depending on what you like. For example, you can label every edge in the diagram of the knot, where I say an edge goes between two crossings, not an arc, but an edge. The arcs are long and continue across over crossings, but the edges are just the edges of the four-valent graph in the plane. If you make a list of all the edges, their names, and you preserve the cyclic orders at the classical crossings, then you can make a list of the classical crossings with their cyclic orders and the names of their edges, and that completely determines the virtual knot, just as well as a Gauss code, and is often useful for computing. Another way to get to a surface immediately is to put a detour, is for every virtual crossing to put a little handle. That will give you a higher genus surface usually than the one I just described, but it's often useful to just look at your virtual knot and think, it's sitting on a surface that way, at least. Moves on virtual knots, as we've discussed before, consist in the usual Reidemeister moves and planar isotopy included in there, and virtual moves, which look like flat Reidemeister moves among virtual crossings, and one extra Reidemeister 3 kind of move, which consists in one little detour by 2 virtual crossings, which is allowed to move across the real crossing. These moves on the right-hand side of the slide, taken all together, imply a detour move like this, where you're allowed to take a consecutive sequence of virtual crossings and cut that arc out and put it somewhere else. Any detour move can be performed by a sequence of these small virtual moves. The small virtual moves are useful for articulating virtual braiding, where if you wish to define the virtual braid group as Roger has, then you need to add some moves to the virtual braid group that are beyond just Reidemeister 2 and the braiding move. And you can do that by essentially adding that one at the bottom and some variations involving the ones here. So the local moves are needed in order to articulate the virtual braid group, but they aren't actually needed in order to articulate virtual knots without braiding, because you can just say detour move for the right-hand side. Another variant of virtual knot theory that is useful and interesting to look at, and there are a lot of variants, but this one I happen to like, is flat virtual knot theory. In flat virtual knot theory, the classical crossings are flat. And the virtual crossings, of course, they're flat also. But the difference here is that virtual crossings can move across flat crossings, as is indicated by the R3 there, or the detour, but not conversely. And this makes it a very non-trivial theory. There are forbidden moves, and we've also discussed that. These forbidden moves are certainly not in the list of things that I've described. But on the other hand, if you were to include F1 but not F2, you would be looking at welded knots or welded braids. And that's a very interesting theory in its own right. If you include both F1 and F2, you can unknot things. So the virtual knot theory can be thought of as virtual diagrams up to virtual equivalents, or oriented Gauss codes up to Reidemeister moves, or as we started, links in thickened surfaces up to one-handle stabilization. The variations that we may encounter, there's more than one, but one variation that's certainly interesting, and we probably should come back to it, and maybe Roger will come back to it, are welded knots, where we keep the over forbidden move. And this is related to braidings of circles in 3 space, and to 4-dimensional tubular braids, and to embeddings of tori in R4. Another variant that I think is interesting is rotational virtual knot theory, and that's virtual knot theory with the detour move restricted to regular homotopy in the plane around the 2-sphere. That means that you do not get to do the virtual 1 flat. Here, you have lots of knots that would not be knotted in the ordinary virtual theory, but they are knotted here, like K in this diagram, because of that little Reidemeister 1 move not disappearing, and the fact that you can't do certain forbidden moves. This ends up being a knot, and some of these others are knots. I say that rotational virtuals are a correct domain for studying quantum link invariants, and we'll come back to that. they're a correct domain because any quantum link invariant that is defined for classical knots extends directly and easily to rotational virtuals. And so if you want to think about a given quantum link invariant, you can extend the domain of topological entities on which it works in this way. And then we had the bracket polynomial. I'm going quickly because we've said a lot of these things before. We've had the bracket model polynomial, and we extend this to virtuals by counting all the loops the same way. That's the first tier of thinking about the bracket in relation to virtuals. So even if you ended up in a state of the bracket with a loop that had a lot of virtual crossings, you just count it the same way as the usual loop value. On the other hand, if you're on a surface, and I may come back with an example of this, but if you're on a surface and you want to look at the bracket polynomial of a knot in the surface, then the loops in the states are curves on the surface. And you can take those curves up to isotopy on the surface and up to what happens to them when they're thrown around by Dane twists on the surface, by surface homeomorphisms. And then you get a bracket which consists in polynomial coefficients multiplied by loop classes and is much stronger than, in principle, much stronger than the abstract bracket that I told you about here. And that bracket is an idea that Heather Dye and I wrote about a long time ago and have examples and a couple of theorems. And it's a good question how strong that is on a surface. So here's a conjecture that if you have a knot in a surface and the surface is of minimal genus for that knot, then this fact is detected by the surface bracket. Could be false, but it would be interesting to see a counterexample to that. So we're talking about the least genus that will hold the virtual knot. What does calculating the bracket look like? Here's a picture. In the case of the knot over there on the right, two crossings, and the states have some loops in them, and each loop is just being regarded as a usual loop value, and you end up with the normalized bracket down there at the bottom. And you see that it's not the case here that every exponent is a multiple of 4, as would be the case for a classical knot. So this tells you it's not classical. So sometimes you can just look at the bracket and tell that it's not classical. Another point that we've made before is that there exist infinitely many non-trivial knots with unit Jones polynomial, virtual knots. Bracket polynomial is unchanged when smoothing flanking virtuals, and I've smoothed flanking virtuals in this picture here. And you see you get an unknot, and that's how I know that this has trivial Jones polynomial. The flanking virtual equivalence here, removing the flanking virtuals, is called Z equivalence, and it's a kind of a flipe. The proof of that was very simple. I'm just reminding you. You just expand the bracket, and you see that the two terms simplify, and you're back at the removal of the flanks. And on the other hand, if you look at the following method, you start with a crossing here, and you rewrite it, which amounts to changing its direction as it goes through the crossing, which means changing the sign of the crossing, without changing its over or under characteristic, if you're thinking about Gauss code. So I think of doing this diagrammatically by walking virtually and then going under and then walking virtually like that, so that this arc is going up rather than down. And then examine what you got. That I call this movement from a classical crossing to this virtualized classical crossing virtualizing the crossing. So if we virtualize a classical crossing and then we smooth it, which gives the same bracket polynomial, and then do a little isotopy on it, we see that it was the same as switching the classical crossing. Now, these are not equivalent virtual knots, but they have the same bracket polynomial, and switching the crossing can simplify a classical knot. So if you started with a classical knot that could be undone by switching one crossing, as was the case for the trefoil, then if you virtualize that one crossing, you will get a knot that has the same bracket polynomial as the original with a switch in the crossing, and that's unknotted. So that's how that works. And if you have a knot, any classical knot, you can choose some subset of crossings and decide that you want to switch them and get an unknot if you choose the right subset. So take an unknotting subset and instead of switching it, virtualize it. And you are now looking at a virtual knot which has unit Jones polynomial. So there are infinitely many virtual knots with unit Jones polynomial. And we want to see that they're all non-trivial if you use this construction. And the way to see that is to understand that the virtualization does not change the involutory quandle, or I'll just call it the IQ, the unoriented quandle of K. And the reason for that is given by this picture. You see, if you're doing the unoriented quandle, then you have A and B, and then the quandle product AB. I'm not writing an exponent here, I'm just writing AB. And then if you virtualize the crossing and examine what happens, you see that the arc A meets B on the other side and goes through, but it doesn't matter because there's no orientation and it comes out AB. And so ignoring the fact that the diagram is a little different, you see that the external effect is exactly the same, and that implies that the IQ of the virtualized diagram is isomorphic to the IQ of the original knot diagram. There are lots of examples of IQ. So an interesting example of IQ is to define it in terms of a group and then define B, A inverse B as the IQ operation. And if you put that relation at every crossing, it corresponds to the fundamental group of the twofold branch covering along the knot. So if you use that IQ, then it would be the case that it detects knottedness because it's a theorem related to the Smith conjecture that classical knots knottedness are detected by the fundamental group of the twofold branch covering along the knot. That means that if you have a non-trivial classical knot and you perform virtualization to make a knot with Jones polynomial equal to 1, it will still be detected as non-trivial by the IQ. That does not prove that it is non-classical. It just proves that it's non-trivial, and we'll have to work harder to prove that it's not classical. This slide is repeating what we already said. And we could define what I have previously called Z-knot theory and what Roger would like to call swap knot theory, which is, I think, maybe a more colorful and better term, to be virtual knot theory modulo the move, the Z move here, the removing or flanking virtual crossing. So we can ask, does classical knot theory embed in virtual knot theory modulo Z equivalence? I don't know the answer to that. It is true that classical knot theory embeds in virtual knot theory. If two classical knots are equivalent by allowing the virtual moves, then they are equivalent by just allowing the usual Reidemeister moves. We didn't discuss the proof of that, and I shan't discuss it today, but it's not hard to prove that by one means or another. But to prove this one seems much harder. maybe it's not true. Now some invariants. Well, one invariant that's worth mentioning for its just strictly for its simplicity and because it reflects a property of virtual knots is the odd rise. In the so I define a crossing in a virtual knot or a classical knot to be odd if in the Gauss code it corresponds to a symbol repeated twice that has an odd number of other symbols in between it. And what that means geometrically, diagrammatically, is that if you take a walk from that crossing, go around the loop that takes you back to that crossing, you will encounter some number of classical crossings. You may encounter some virtual crossings, but you won't count them. And you're going to encounter an odd number of crossings as you take that walk, if the crossing is odd. This doesn't happen for classical diagrams, but as you see, looking at this picture, it's quite clear that it can happen for virtual crossings because virtual crossings correspond to the residues that would add up to an even number of crossings of lines going through the loop. And there may be an odd number of them, and as a result, you'll have an odd number of classical crossings that you see. So we have odd crossings and parity, and this is ubiquitous across lots of considerations about virtual knots, that the parity is important. We'll see it again and again. In the case of the odd rise, you just take the sum of the signs of the odd crossings. And that is invariant under virtual moves, all of them. And unlike the usual classical ride, which is the sum of the signs of all the crossings, this is invariant under even the first Reidemeister move. You see the first Reidemeister move, the little curl, is a 1. It would be like a 1, and then nothing, and then the 1 again, and nothing is even. So the odd ride is invariant under the first Reidemeister move. And you can do an exercise for yourself and check that it's invariant under 2 and 3 as well. And what properties does this number have? Well, it's an invariant. It's equal to 0 if you have a classical knot. And if you take the mirror image of a knot, you get the negative of it because you switched all the crossing signs. So we have just proved that this gadget up here, this virtual trefoil, so-called, is inequivalent to its mirror image and not classical because its j is -2. Its mirror image has j equal to 2. So that's the simplest invariant I know of virtual knots. And it's pleasant that the ride actually is an invariant of knots in this way, odd ride. I'll come to some more invariants in a moment, but I want to define virtual knot cobordism. So I have illustrated here some changes to diagrams in the form of going through a saddle point or having a birth or a death. So I'm going to allow such things into the brew and say that two knots are cobordant, virtual knots are cobordant, if you can get from one to the other by the usual moves plus some sequence of saddle replacements, which means that you take an oriented line and an oppositely oriented line and let it go through a saddle, thereby preserving an orientation on the result. Or an unknotted circle can die out, be capped off with a disc, or it can, I got my timeline running up. So this is the birth of an unknotted, or be born. And you think of this as a surface in four space when you're doing classical knot theory. You can think of this as a certain kind of surface in four space for virtual knot theory as well. But if you do, then you have to think of one-dimensional seams in that surface corresponding to the virtual crossings, if you want to think about it in an immersed way, or you have to think about special surfaces in 4 space in another way for making it more geometric. It's not necessary at the outset to worry about the nature of these surfaces. You can just define 2 knots to be cobordant if you can get from one to another by saddles, births, and deaths. When you do that, you generate a surface abstractly through your production of saddles, births, and deaths. So for example, if I had 2 circles and I went through a saddle point, I would get a single circle and I've generated a bit of genus 0. But if I went through 2 saddle points like this, going to 2 circles and back to 1, then I generate a little bit of genus in an abstract surface. That abstract surface is actually embedded in 4 space in the usual classical picture, and I will say it's virtually embedded in 4 space, and we can talk about that later as to what it would mean, what kind of surface in what kind of 4 space. You may also wish to think of the surface on which the knot is drawn cross the unit interval, cross an extra unit interval, thickened surface cross unit interval, cross a 4-dimensional unit interval, and think of the cobordisms as occurring there. But as I said, we're just going to think about the equivalence relation in terms of adding saddle moves and births and deaths. And then there is the associated surface between 2 cobordant knots or links. And we can talk about the genus of that surface. And we can ask whether a given virtual knot bounds a surface of genus G for some G, or whether it's cobordant through a surface of genus G. So here's an example. I call this knot over here the virtual stevedores knot, because I'm mimicking a cobordism that you might find in other places, like in Fox's Quick Trip, where he uses the stevedores knot and shows that it's a slice knot. Here, some crossings are virtual. And if you watch the orientation, you will see that this point here, that I'm pointing at, I hope you see my pointer, is going in the opposite direction. It's going in the same direction as this one. If I put a little virtual twist there, they're going in opposite directions, and they are candidates for a saddle point. So I go through the saddle point. There, I've gone through the saddle point. And then looking at this carefully, you see this component here. And that component has 3 consecutive virtual crossings that I'm moving my arrow along. And I can do a detour move, and I can cut here and reconnect right there. And so that's virtually equivalent by a detour move to this one. And that one's unlinked. And so it becomes 2 circles, and they can both die. And so the virtual surface that it bounds is a disk. 1 saddle, 2 deaths. It's a disk. So that says that the virtual stevedore is slice. Now you want to prove that the virtual stevedore is actually a non-trivial knot, and that requires some extra work. I won't do it today, but that's a good example of a non-trivial slice knot in virtual context. I've rewritten it in some other form here to make it look like a ribbon knot. I think I won't bother you with that. I do want to prove that the virtual stevedore is not classical. It turns out, if you calculate its bracket polynomial, that it doesn't show you that it's not classical from the bracket polynomial. So this is an example, and I'm not going to walk through the details of it, of looking at all the loops on the torus. You see, here's the virtual stevedore sitting on its torus. It is on a torus because of those virtual crossings that were flanking of the twists there, and you can draw it on the torus this way. And then I'm claiming that that's the least genus that this virtual knot can achieve. And so I do the bracket, which means I expand the bracket on the torus, and I look at all of these loops that come about and examine their isotopy classes and think about what's going on there. And if you do that, you will conclude that it couldn't possibly have been moved off the handle of the torus. Not possible because of the isotopy classes of the curves. Well, that's an example of using surface bracket and an example of the conjecture that I was mentioning. Now, what about mirror images and cobordisms? Here's the vertical mirror image of K over there on the right and K on the left. And I've reversed the orientation so I can let them go through a saddle and take a connected sum. Connected sum, by the way, is not defined. It's only defined as this particular connected sum by cutting out two arcs and putting the thing together. In general, connected sum is not defined globally for virtual knots because of the forbidden move, among other things, that will not allow you to move the factors around very much. But here is a standard connected sum of K and its mirror image. And I claim it's slice. And the slicing of it can be done in the same way that you would slice in the classical case. You look for saddle points to go through. And if you go through a couple of saddles, in this case, you end up with some curves which slide out from one another and become a bunch of individual curves and all bound disks. So I'm going through saddles in such a way that I don't generate any genus and end up with a slicing. Now, to repeat, we say that K is concordant to K prime if there exists a cobordism of genus 0. And that's well defined. You go through the cobordism step by step, a bunch of saddle points and some births and deaths, and it gives you the virtual surface, the four-ball surface. And the genus of that is 0, means that we're looking at a concordance. And a virtual knot is said to be sliced if it's concordant to the unknot. Now, what about some standard surfaces that a virtual knot might bound? Well, in classical knot theory, we have the Seifert surface. And you recall Seifert's algorithm. You take the knot and you smooth every crossing in the standard way according to the orientation. You get the Seifert circuits or the Seifert circles. And then you bound every one of them with a disk in 3-space. You may have to use 3-space, not just the diagram, to get them nested correctly. And you put the twists back, little bits of ribbon, and you obtain the oriented Seifert surface for the knot. And you can work out the genus of that surface, and you can ask many questions about surfaces bounding knots in 3-space. But if it's a virtual knot, this crossing here, for example, might be virtual, and then the Seifert algorithm doesn't seem to be giving you a surface anymore. And you can't think about the way such a surface is embedded in 3-space. You can, under appropriate circumstances, think about Seifert surfaces for knots that are embedded in a thickened surface, but I wish to think about it in this abstract framework, and there I don't have it. On the other hand, there's another way to think about the Seifert surface, and I call this the classical cobordism surface. At every crossing, there are two lines which go in opposite directions, and you can do a saddle. You do a saddle at every line. This is the mimic of Seifert's construction. You do a saddle at every line, and you get a collection of curves. They are exactly the same as the Seifert circles, except there are little curly bits along some of them. And then, having done those saddles, you bound those discs off into the 4-ball. You already went through saddles into the 4-ball, and then you bound discs further into the 4-ball, and you obtain a surface that bounds this knot in the 3-ball, in the 3-through surface into the 4-ball. You obtain a surface embedded in the foreball, transverse to the boundary of the foreball, and meeting the boundary in the knot. And this can be done for any classical knot. And if you examine this carefully, you see that the surface you created is indeed the Seifert surface by Seifert's algorithm, but pushed gently into the foreball, making it transverse at the boundary. And so it is a surface that bounds the knot in the foreball. It's always there, and the knot may bound a simpler surface in the foreball. But we have a standard surface, the pushed-in Seifert surface, or the cobordism Seifert surface, that is in the foreball already. And you see that I can do this for virtual knots. Here's my virtual knot, and I perform a little saddle at all the virtual crossings, at all the classical crossings. And then I have some circles, in this case only one, and I bound it off. And I have a cobordism to the empty knot. I have a surface that bounds this knot. And what is the genius of this? Well, a little Euler characteristic thinking will tell you that the genius of this is 1/2 of minus r plus n plus 1, where r is the number of Seifert circles, where these are the Seifert circles. You do go through the saddles, and then you get some circles. Those are the Seifert circles by definition. Minus r plus n, where n is the number of classical crossings in the knot. It's the same as the Seifert genus, except that we have different counts for Seifert circles. And so in this case, for example, we have a surface of genus 1. So we always have this. This is a cobordism that's of interest because, you see, now we can ask, what is the least genus that a virtual knot bounds in the virtual foreball? I speak of it as though it were really embedded in a foreball, just for the sake of language. You understand it is what is the least abstract surface that can be traced by doing saddles and births and deaths. And we have one at least with us, so it can't be any larger than this if you're looking for the minimum. So here's an example where I'm looking at it. I take this knot and I go through a saddle here, and I get this little link, and then I go through another saddle here, and I get this curve, and then I bound it off. Now, I did it sequentially so you can see what happened. And you can see that when I went through the first one, I went to 2 components, and then I went back from 2 components to 1 and bounded it off. And so I ended up with genus 1, just the same as my Euler characteristic calculation. So using that concept, Heather Dye and Aaron Kastner and I proved the following generalization of Rasmussen's theorem, giving the foreball genus of a positive virtual knot. The theorem is that if you have a positive virtual knot, then the foreball genus, by which I mean the least genus among those surfaces I've described, is actually equal to the Seifert genus, where we form the cobordism Seifert surface. And the proof of this uses some Kauffman-Lee homology. And I'm going to, in the course of time, after this lecture and with some help of time, tell you about Kauffman homology for virtual knots and then how we prove this theorem. So this is a nice result. The original Rasmussen result is exactly the same result for positive classical knots. If you have a positive, meaning all the crossings in the virtual knot are positive, then the same theorem works, and you can find the least genus in the foreball. Continuing. Classical spanning surfaces simplify by passing bands. This is a very nice bit of classical knot theory that is, I like to mention it just because it's so pleasant. Here's a classical knot, and you can form the spanning surface and think of it as a disk with attached bands. You can push the cipher construction around until it looks like this if you want. And then you will allow yourself to take the bands and switch them, just like switching or crossing. Maybe I drew that somewhere, yes. So I have a band, I've only drawn the boundaries of the band, oppositely oriented directions, and I have two of them and another two of them, and I can switch them all. That's switching the bands on the surface. If you switch the bands, then a certain quadratic form, which I shall not define here, remains the same because it's a mod 2 form and becomes an invariant of switching the bands. And by switching the bands, you can simplify the surface enormously, and you can show that any classical knot through this band switching is equivalent either to a trefoil or an unknot. And that corresponds to the ARF invariant of the corresponding quadratic form. So there is an invariant of classical knots called the ARF invariant, and two classical knots are equivalent by this pass move if and only if they have the same ARF invariant. And knots with ARF invariant 1 are not slice. So this is a bit of classical knot theory. It would be interesting to understand this same relation for virtual knots, but we don't understand it very well. It isn't going to be just two classes anymore. In fact, there will be infinitely many classes. And it's a nice problem to understand it better. Micah Chrisman has a paper about this, and I'm going to make a remark or two about it as we go along. And now we get to some examples. Here's the Kashino diagram, which Roger mentioned a while back. It has a unit Jones polynomial, and it has trivial fundamental group, but it is detected by the biquandle, as Roger explained. It's a curious customer, an example of a connected sum of two virtual knots where the individual summands are trivial. It's just showing you how undefined connected sum is. I say that the Kashino is not pass trivial. Remember what pass means. Pass is a equivalence relation we're going to define on any virtual knots by allowing this switch. And in classical knots, there are two classes, but the Kashino is not pass trivial because, in fact, it's a non-trivial flat virtual knot. And we're going to see a proof of that. And its flat class is its pass class because passing doesn't affect it as a flat. There is no over or under to switch. So if we prove that Kashino is a non-trivial flat, then we have, in fact, given an example of somebody that can't be passed. So I think the first invariant that's new today will be the last invariant I talk about today, given the amount of time. This is a variant of the bracket due to Vasily Manturov. And Vasily says, separate into even and odd crossings. Take your diagram at the very beginning and make graphical nodes out of all the odd crossings. Having done that, expand the bracket on the even crossings. Don't worry anymore about what's even and what's odd after you do this. Just do away with all the odd crossings at the beginning by making them into nodes. The resulting bracket polynomial, which consists in polynomials times graphs, will be invariant if you reduce all your graphs by Reidemeister 2 moves on the graphs as indicated. Two graphical nodes forming a two-sided region can be eliminated, and you reduce the graphs. You don't make them more complicated. You simply reduce them if it's possible to reduce them. So consider that. Now this is invariant under all the virtual moves. I guess I leave it to you as an exercise. And here's the Kashino, and every crossing is odd. And so they all get notified. And then you have to examine this graph here and convince yourself that there are no reducing Reidemeister 2 moves. Now remember, there is something to convince yourself of, because virtual crossings can skitter around through the lines that you see, and you have to sweep them away. You have to make sure that it's really true that there are no there are no 2 moves that will reduce this graph. And having convinced yourself of that, you're done. The invariant is this graph. No polynomials, nothing. So it's a one-step process. And so if you go through the exercise of proving that the parity bracket is indeed an invariant, then the Kishino is its own invariant, and we're done. It's non-trivial. And furthermore, this is a flat invariant if you take a equal to 1. And so it didn't matter that I had crossings set like this. You can just think of it as a flat virtual knot, and the definitions are the same. All the crossings are still odd, and the invariant is still the graph. So that's all I needed to show that that this was non-trivial from the point of view of bandpassing, and it's all I need to do to show that the Kishino knot is non-trivial in the category flat or otherwise. Incidentally, Rogers showed us last time that the Kishino knot was non-trivial by using the biquandle. And you might wonder, in the light of what I just said, what about the flat? Can you prove that using the biquandle? And there is a paper by Sam Nelson and Alison Henrik from about 2008 where they define a semiquandle for flat virtual knots. You'll find it easily on the archive. And in that paper, they prove that the flat Kishino is non-trivial. So you can do a semi-biquandle, for flat virtuals. You may be interested in looking at that. Oh, what about this 2 move? One way to deal with the 2 move is to look at it in the Gauss code. You see, if you went to the Gauss code and drew the 2 move, then you would see BA and then BA again later in the code, or BA and then later AB, and you would see 2 chords like this, nothing between the bases of the chords. And you would be allowed to remove that if you were doing a 2 move. So one way to become quite clear that something can't be reduced by 2 moves is to go and draw the Gauss code and look carefully at the Gauss code. Here's the Gauss code of the Kishino. By using that idea, you can produce a lot of examples. So for example, here is a flat diagram with all odd crossings, and I just make sure they're odd by looking at the intersection number of the chords with each other. So every chord has an odd number of other chords intersecting it, and that makes it into an odd crossing in the corresponding diagram. So this guy here has all odd crossings, and it doesn't have any reducing 2 moves, and so it also will be non-trivial by the parity bracket. And so in a certain form of examples, you can go ahead and make infinitely many examples. So for example, I went a little farther, making odd crossings. And this guy, which I probably didn't draw an ordinary diagram for, will also be non-trivial flat. And so the combinatorics comes in and does a lot of work for you at this stage. Here's another example. You'll notice that I have seemingly digressed from the virtual cobordism part, except for the bandpassing. And as we continue, but we will probably stop before I continue very much, we'll go back to the cobordism question. Here's a knot, which for some reason we called S3, was found by Slavik Jablan, and it has unit Jones polynomial, and it is not swap equivalent to a classical knot. So that's an example of this phenomenon of unit Jones polynomial occurring outside of the range of examples that we already produced. And we're going to prove this is not Z equivalent to a classical knot by first examining its parity bracket. So here's the diagram, and I have labeled the crossings that are odd and the crossing that is even. One crossing is even and 4 are odd. So this is what would happen if you looked at the parity bracket of this. You see, you have to notify these, but then you have 2 of these. You smooth it this way, or you smooth it that way. Smoothing it this way, it all slips apart. Those 2 moves really do reduce the graph, and you get a circle. But smoothing it the other way, you get somebody which is non-trivial, and that proves that it's a non-trivial knot, even though its Jones polynomial is trivial. On the other hand, if you were going to do Z moves on it, then you would have to consider, you would have to make the parity bracket invariant under the Z move as well. And that means that you have to add to the reductions switching a virtual crossing with a node like this. And then you have to convince yourself that there is no reduction of this graph from Reidemeister 2 moves or switching crossings with nodes, which there is not. And so that means that this original knot could not have been reduced under the Z move because the parity bracket that we've defined, this reduced parity bracket, it will be invariant under the Z move. And so we have an example in this way of a knot with Jones polynomial 1 that is not invariant. Another way to detect it is to use the arrow polynomial, which I haven't talked about, and that's what this is about. But this has trivial Jones polynomial. So that means that there are a lot of these people out there with trivial Jones polynomial that don't come from our simple construction, and we don't know very much about them. The next thing I'm going to talk about, but I think perhaps I will just show you this slide and stop, is the index polynomial. And the index polynomial is a way of looking at a kind of generalized parity and getting an invariant of virtual knots. It's very simple. And it will detect the knot with Jones polynomial 1 that we had before, thereby completing the circle of showing that that knot is non-classical. But it also is the case that this invariant is an invariant of knot concordance. So that's one of the reasons for having introduced knot cobordism, so that at the point when we look at this invariant, we can think about how it behaves under cobordisms as well as other things about it. So I'm going to tell you the definition and then stop. The definition, as I like to give it for the sake of calculation at least, is the following. You take your diagram and you label the arcs in the diagram, the edges in the diagram of a flat diagram. So you take a flat diagram and you label its edges. Now, I see I was being a little uncareful about what I call an edge. Here's the flat diagram. This is an edge going from one classical crossing to another. Here is an arc that goes from one classical crossing to another. That is also an edge. Even if it goes through a virtual crossing, I don't regard that as creating new edges. So the edges are the edges of the abstract graph. Okay, now you label the edges with integers. Say you start labeling this edge with 0, and you go through a crossing, and the arrow of the crossing you went through goes to the left, you decrement by 1. If you go through a crossing and the arrow that you meet goes to the right, you increment by 1. You then walk through the diagram and label it. having labeled it, you assign, I hope I have a picture of this. I see, I kept it very abbreviated. Yes, too abbreviated. Let's leave this slideshow and I'm going to just talk about it for a moment by drawing, and then we'll stop. Okay. So I'm in this flat diagram and I'm labeling it. Maybe this is labeled A to begin with and this is labeled B. So this would be labeled A plus 1. And this would be labeled B minus 1. And then at the top here of the crossing, I call W plus, the plus weight, equal to left index minus right index. And at the bottom, I call the minus weight equal to left index minus right index. As you see, the plus weight is B minus A minus 1, and the minus weight is A minus B plus 1, which is equal to minus the plus weight. But nevertheless, for bookkeeping purposes, it's good to have them both. If I have an ordinary crossing in some diagram that I have labeled in this fashion, then I define W of that crossing to be equal to W sub sine of the crossing. So that means W plus if it's a plus crossing and W minus if it's a minus crossing. And then we're going to define a polynomial pk by the sum over the crossings, the sine of the crossing multiplied by t to the weight of the crossing minus 1. And I call that the index polynomial. And it is a slight variant of polynomials that were defined by other people as well. For example, Alison Henrik in her thesis defined a polynomial, but she had absolute value here. Cheng defined it by initially by summing over the odd crossings, and so on. And Heather Dye defined one using Gauss codes. It's a natural enough idea and it comes up. And this is an invariant of the virtual knot. And it's a concordance invariant. If two virtual knots are concordant to one another, you'll get the same polynomial. And you can think about the Sillief invariance in relation to it and a number of other things. It's very easy to calculate, as you see, in principle. And so that's what I will be talking about starting next time. I'll stop now.
Well, thanks, Lou. Very nice talk. Are there any questions? I've got lots of questions. Did that last slide define a BIRAC? Was that a BIRAC?
What do you mean? The labeling by integers?
Labeling, does that give a?
Yeah, it defines a biquandral. It does. Yeah.
Yeah.
Very simple one.
Yeah. Yeah. Well,
in the paper I wrote, I analyzed that a bit. You might see more if you look at it through your biquandral eyes.
Yeah. Okay. Okay. Another question is why call them rotational virtual knots?
I call them. My reason for calling them rotational virtual knots is because the you have to keep track of the rotational degree of the plane curves, the Whitney degree of the plane curves. It is not a framing, it's a Whitney degree consideration. And that's why I call them rotational.
Okay. Some time ago, I read a paper with Cervantes on the ARF invariant. Did you know that, or did you know that paper?
I'm sorry, that you wrote a paper about the ARF invariant?
Yeah, with Cervantes.
And what did you do in your paper?
You know, I can't remember.
Well, find it and send it to me. I've been fascinated by the ARF invariant since the beginning of time.
Yeah, it was his thesis, and we published it in the Oxford Quarterly Journal. Anyway, one final thing. Sorry to hog all this. I thought I saw a Massey product in you know, you've got. Is this a free knot? You know, you did the you did the chord diagram of this knot, and then you generalized it, and it looks as though there was a Massey product there, but I don't know. Have you thought about that?
I have not thought about Massey products in the virtual context, so it'd be interesting to do that.
Yeah, I'll have to think about that.
We could go back to the Borromean rings and take some virtual version of Borromean rings and ask whether you can detect them with something like a Massey product. Yeah.
Are there any other questions? Have I shut everybody up? Well, okay. I don't know if is Dale still there, or?
Yes, I'm here.
Dale, you're speaking Friday, right?
Yeah.
I will be speaking Friday.
Great.
And that's great. Did you?
I have a technical question, Lou.
Yeah.
How did you get your mouse to work on Keynote?
How did I get?
Your mouse to work when you were using Keynote.
I wasn't on Keynote. I had switched to a graphics tablet and a paint program when I was drawing stuff.
No, but you were pointing while you were on Keynote.
Oh, I wasn't on Keynote then. I was in a PDF.
Ah, okay. I see.
Yeah.
Okay, so that seems like there's no more questions. And
oh, I see. Just a moment there. Yeah.
Oh,
I accidentally pressed the share screen button.
Technical stuff. Okay, that's very good. And we'll see you all hopefully on Friday when Dale will be talking. So bye for now.
Thank you.
Bye-bye.